If you recall Kepler's second law, equal area and equal time, we had L over m times time is equal to the integral from some initial angle to some final angle, r squared d theta. If we're looking at a full orbit, then the time it takes to go around is the period. And so we're left with L over m times the period is equal to, well, doing a full circle here, so basically the integral from 0 to 2 pi of r squared d theta, which is just the area of an ellipse, 2 pi ab. Solving for the period, so the period is equal to 2 pi ab m over L. I know that L, as seen in a previous video, we have this relationship right here, that L squared over mx squared times a over b squared is equal to gms. Probably a faster way of doing that one. So L squared is equal to gms mx squared b squared over a. So let's go ahead and, instead of doing the square root of that, let's square this out. So I have t squared is equal to 4 pi squared a squared b squared m squared, that's mass of x, over this whole mess here. So this is g mass of sun mx squared b squared over a. Let's get rid of what we can. So b squared and b squared cancel out, mx squared and mx squared cancel out, and I'm left with 4 pi squared a cubed, when that a comes up, over g mass of the sun. In other words, t squared over a cubed is equal to 4 pi squared over g mass of the sun, or g mass of the sun over 4 pi squared is equal to a cubed over t squared. And that's Kepler's third law. The fact that if you look at the length, the size of the semi-major axis, in other words, half of the major axis, cubed over the time it takes to go all the way around squared is going to be equal to a constant. And this recognize that the planet that is orbiting the sun has no bearing on this. And through this then, g we have found that we know experimentally, we can actually now calculate mass of the sun, because that is going to be this ratio, a cubed over t squared, times 4 pi squared over big G.